Hello, welcome to Lesson 10. Today we're going to be talking about the basics of regression analysis. So we'll cover simple regression and regression with a dummy variable. This video is part of a lecture series called Applied Statistics Using Programming, brought to you from Sogang University. My name is Dr. Ian. Let's get started. Okay, so let's talk about simple regression analysis. Before we talk about regression, let's talk about something a little bit more simple called correlation. Let's say we have a data set. In this data set, I have the height and weight of a number of celebrities. What patterns do you see in this data? We see that we have both Western and Korean actors. Some are in films, some are in dramas, some are actually just entertainers. Do you see any other patterns with this data? I also see that a lot of the Western actors are coming from DC and Marvel universe. Generally, they tend to be action stars, so probably this might have some impact when we're analyzing the height and weight of these people. When we look at the Korean actors, some of the Korean actors are also in action movies, but others are from drama. So the types of people might be a little bit different when we start to analyze the patterns in this data. Okay, so keep that in mind when we're looking at our analysis results. So in this data, we have 33 people. What is the relationship between their height and weight? How can we measure this relationship? One way to measure this relationship is to look at the linear relationship through correlation. Correlation ranges from +1, meaning a perfect positive correlation, to -1, meaning a perfectly linear negative relationship, where as one variable increases, the other decreases. In this case, we'll name one variable as x, we'll call weight as x, and one variable as y arbitrarily. In this case, y is the height. Okay, so as we mentioned throughout this lecture series, there is a difference between the population and the sample. What are some of the differences between population and sample? The population is the entire target of subjects that we're talking about, whereas the sample is a much smaller subset from that population. The population is either incredibly difficult to measure or sometimes simply impossible to measure. So you should consider the population as some kind of theoretically perfect solution that we don't actually know, but we can infer about that population using our sample. Why can we make inferences using a sample? Because if we use good sampling techniques, we can use a smaller amount of data to make inferences about other individuals in the bigger population. So keep that in mind when we look at our sample. Consider, what is the population that this sample is part of? Is this sample just part of all males? Is this sample just celebrities? Is this sample a specific type of celebrity? So keep that in mind as we go forward. Okay, so how can we calculate this Pearson-R correlation? This formula here is used for the sample, and because we have a data set, that data set is our sample. So we can use this long formula to calculate the correlation between our x variable weight and our y variable height. In this example, my correlation is 0.69. If we actually make the calculations, we end up with these specific numbers down here, and that all equals 0.69. Now, what type of relationship is that? Is it perfectly positive? Is it perfectly negative? It's neither. It is a positive number because it's between 0 and 1, and it's fairly quite highly positive, 0.69. So what this means is we have a roughly positive linear relationship if we were to draw a line through our data here. So how about simple regression? Simple regression uses this equation here. Again, there is theoretically a perfect model that looks like this that would explain the entire population. However, because we need to use a sample, we're using the estimated regression equation that you see on the left, because this one reflects dealing with sample data. What is our sample data? In this example, our sample data is X and Y. What is our X random variable? This is the weight of the celebrities. What is our Y? This is the height of celebrities. So what this equation says is, if I know a value beta 0 and beta 1, which we will calculate, then I can predict, if I have anybody's weight, I can predict their height using this data, using this model that we've created. Okay, so if you look at Y, we see a little hat on top. We call this Y hat. It looks like a little hat. Cute. Y hat means that it is a prediction of Y. X means that it is an actual value of X. These other two coefficients, beta 0 and beta 1, we're going to calculate. So let's try to calculate beta 1 first, because we need to know beta 1 to understand how to calculate beta 0. What does beta 1 tell us? Beta 1 tells us for every increase in X, beta 1 is the amount of change in Y that we should expect. In other words, if X increases by 1, someone's weight increases by 1 kilogram, what is the expectation of their height? Okay, so we can describe the relationship between one dependent variable, Y, and one explanatory variable, sometimes these are called independent variables, X, using simple regression. Simple regression just means we have one independent variable and one dependent variable. Okay, so following this formula, we can simply input these values into R. Now that we know the beta 1 value, we can calculate beta 0. All we have to do is take our sample mean of X and our sample mean of Y and run this calculation quite simply, and that will give us beta 0. What does beta 0 tell us? Beta 0, which we sometimes call the intercept, is if we drew a line through our data, where would that line intercept the point x0? In other words, where would it cross the axis? Where would it cross the y-axis? If we calculate this, we get this equation here, 158 plus 0.32. That means if my weight is 0, then my height should be 158. That doesn't exactly make sense. However, we shouldn't consider every value on this line to be a realistic value. Okay, so this equation creates this line. What does this line tell us? This line tells us if we know the X value, let's say your weight is 80 kilograms, we can track onto this regression line and predict that the height would be somewhere around 180, a little bit more than 180 centimeters, given this data set. So this is our beta 0. This is where the regression line, this red line, crosses x equals 0. And for every 1 kilogram increase in weight, x, we should expect a 0.32 centimeter increase in height, y. Okay, so how do we know if our model fits? How do we test if our regression model is a good model or not? We can use R squared. R squared tells us how well our model fits the data. So R squared ranges from 1 to 0. 0 means our model doesn't explain the data at all. 1 means our model perfectly predicts y given x. So it doesn't matter whether that relationship is positive or negative. The R squared ranges from 0, meaning it doesn't fit the data, to 1, meaning our data perfectly fits. Is there a cutoff? I've taken a lot of social science courses where the professors have told me if it's below 0.6, we can't use it. Or if it's below 0.7 or some other arbitrary threshold, we shouldn't use the model. This is not necessarily true. It depends on the domain where you're using this. In other words, it depends on what you're measuring. If there's something with a lot of variation, let's say the stock market, and your model gives you a really low R squared, let's say, I don't know, 0.2, 0.2 would be a very large amount of explanation for the variation in the stock market. That might mean actually you have a good model, even though your R squared is very small. So if anybody tells you that there's a specific threshold, take it with a grain of salt. It depends on what you're measuring. Here is the R squared for our data here. We have 0.47. That's our R squared. Is it very high? It's not particularly high. Is it low? Again, it depends on what we're measuring and how much information we have. In this case, I would probably consider this a little bit on the lower side. Okay, so we can create an ANOVA table here, even though we're not doing ANOVA, we're doing regression. So the regression model also uses an F statistic, and we get a p-value for that overall F statistic. We call this the overall test. This tells us whether our regression is worth using or not. What are the model assumptions of regression? We assume that it has a linear relationship. Regression is only used to make a linear line. So if we have an arc or some other shape, then, or a parabola or some other shape, then we shouldn't be using a regression model. There are many other models that are more suitable for this type of relationship. We also assume a normality of error. This means that when we draw our line, we assume that the error follows a normal distribution above and below that line. In other words, our prediction using this line should be very close to the line following a normal distribution. There should be no autocorrelation. Autocorrelation happens when our observations are not independent. What autocorrelation is usually referring to is some kind of time series data. We should not be using regression with time series data. Homoscedasticity is an assumption of a regression model that basically tells us the error is consistent along our entire regression line. So we don't have a fanning out pattern. We call this heteroscedasticity, meaning that it's not the same throughout the line. Our error increases at one end of the regression line or the other. We also have heteroscedasticity in the other direction, where it fans out in the bottom of the line and gets narrower. Or we could have kind of an hourglass shape where it fans out on either end. If we see this relationship, what does it mean? One, it means we probably shouldn't use regression, but it also tells us that if we are using regression, we're probably missing something. This happens when there's another variable affecting our model that we haven't included into the model. So if you have a problem with homoscedasticity, meaning you have a heteroscedasticity of your error across your line, that probably means you're missing some important variable that would explain this relationship. How can we improve this model? Well, we can see that some of these points are close to the line. If the points are close to the line, that means we predicted them well. If the points are far from the line, it means we did a poorer prediction using this model. Do we see any data that might be causing an issue? Well, this one is very far from the line. So if we deleted it, what would happen to our line? Our line might slightly move up because we're deleting this value. Would that make a better model? Maybe, but there's another point that's causing a bigger issue. If we look over here, this point has high leverage and high error. High error refers to how far this point is from the line. It's very far from the line. This other point here was also far from the line, but because it's in the middle of the line, it doesn't have high leverage. So what is leverage? Leverage is like if you're on a seesaw and you pull on the end of the seesaw, it creates a strong change in that seesaw. However, if you're really close to the middle of the seesaw and you press, you need a lot more pressure to push that seesaw down. In other words, a data point with high leverage, like this one here, is pulling the line down, which might be inconsistent with the data that you have. So who is that? That's Gang Ho-dong. So what should we do in this example? In our example, almost everybody is a celebrity actor. However, I suppose Gang Ho-dong does some acting and he's an entertainer, but he's well known for first being a siram, being a wrestling player, athlete, and then becoming an entertainer later. So I would say, given our data, perhaps he doesn't fit the rest of our data very well. In that case, I would recommend to delete that observation because it's an outlier. It's pulling our line in a direction that doesn't help make our model better. So if we delete that outlier, we see that our line changes slightly, and it's much better at predicting some of these. It's much better at predicting some of these people up here and down in this area. I think overall we might have a better model. So with Gang Ho-dong in our data, we have a correlation of 0.69 and our R squared is 0.47. If we delete the outlier, we get an R squared of much higher value, 0.61. In other words, that outlier was causing a problem for our model fit. By deleting him, our model fit increased. Now, actually, if I went through my data and simply deleted each case where someone is far from the line, my R squared would probably get better and better and better until I only have 2 people left in my data set. So how do we know when to stop deleting outliers? We should only delete outliers one by one. Every time you delete an outlier, your line, your slope will change slightly depending on where you deleted that individual from. So how many outliers should we delete? Let's say we delete one outlier, our slope is going to change. Now, when our slope changes, now it's created a new outlier. So what if we delete that? Then our slope changes again, possibly could create another outlier. We could follow this process until we're stuck with just 2 data points and a perfect R squared, because drawing a line between 2 points will give you a perfect model. But what's the problem? That's not a very useful model. So consider whether it makes sense to delete an outlier based on the theoretical reasoning. What are you going to use your model for? Does this person represent the population that you're trying to include, or is it an outlier from that population? So we can do one more thing to improve this model, which is to include more variables. Let's talk about dummy variables very briefly. This is just meant to be an introduction to the concept of dummy variables and how it will affect your model. Dummy variables are categorical variables in a regression equation. The difference between a baseline category and every other category is calculated. They maintain the same slope, but change the y-intercept for each category. Note that there are several popular ways to write the same formula below. Sometimes A is used, sometimes alpha, sometimes D is used for dummy, okay? But the equation looks as follows. We have our original regression equation, and now we're adding one more piece of information, which is a treatment group or a dummy variable, categories. We have 2 categories in this data. What are they? We have Western actors and Korean actors. Should we expect that there's a difference between them? Probably, because the types of movies or entertainment that they're in is quite different. Some are many action stars, some are in dramas and other things. So let's incorporate that information into our model. If I were to color my scatter plot by which country my actors are from, either they're Korean or non-Korean, I know the Western actors are not strictly Western. In this case, we see a bit of a pattern here. The Korean actors, shown in blue here, are in this little cluster over here, whereas the Western actors are these red dots here. It seems that there's a slight difference between these two groups. If we were to draw a regression line through these groups, we see that the blue line is representing the Korean actors, the red line is representing the Western actors. We see that that red line fits the Western actors much better, the blue line fits the Korean actors much better than the overall regression line that we had before. In this case, our R squared increased quite a lot. And let's look at our equation. Our equation is intercept plus beta 1 times weight plus A, some other coefficient related to our dummy variable. All right, so what is our dummy variable? It's whether the actor is Western or non-Western. In this case, we can restate our equation as follows. What was our coefficient? Our intercept was 147. Our coefficient for beta 1 is 0.51 times the weight of each individual, minus 6 times whether they're Western or not. If it's a Western actor, this value is going to be 1. If they're a Korean actor, this value is going to be 0. So what does that do to our equation? Let's say I have two people who have the same weight. Well, I would solve this part of the equation. If one of those people is Western, this would be 1. So that would mean we would calculate their height. Let's say their height is 80 centimeters. And then minus 6 times 1, so minus 6 centimeters. Now we have 74 centimeters. Our prediction would be 74 centimeters. Let's take the other example here. Let's say we calculate the same person and we estimate that their height is 180, but they're Korean, so this would be 0, not 1. So we would say minus 6 times 0. What's 6 times 0? 0. In other words, in the case that we're looking at a Korean actor, this would be 0, so this part of the equation would not be counted, so our equation would simply be 180. So what does this dummy variable do? If the observation is in the reference group, meaning the group where this dummy variable is 0, it's going to be the same equation minus this part, minus the dummy variable part of our regression equation. If it's another group, let's say the group is all Westerner in this example, then that would be 1. Then we would incorporate some change to our y variable, which is represented by this a or alpha value here. Okay. So in other words, if we had a Westerner, we would have a 1 and we would multiply that by a. If we didn't, we would be talking about the reference group, which basically means 0, and this part of the equation is not included. Multiple regression refers to having more than one variable. So in this case, we might have 1, 2, 3, as many variables as you need to estimate this regression equation. Okay, this becomes a lot more complicated. Why? Because instead of being able to show the result on a scatter plot where we have an x and a y variable, if we have, let's say, 10 variables, if we have, for example, 10 independent variables, we cannot show the result in 10 dimensions or else we wouldn't be able to read it. So one of the more difficult parts of multiple regression is testing using statistical tests to check whether the fitness of your model is matching our regression equation or not, and whether it's following the assumptions of regression. What are the assumptions of multiple regression? Everything is almost the same except we have this extra assumption, no or little multicollinearity. It means that our independent variables should not be multicollinearily related to each other for predicting y. In other words, if we have multicollinearity, it means multiple independent variables are giving the same information, so we would want to eliminate those variables from our model. We should follow Occam's razor and use a simpler model is better approach. Okay, so here's an example of a regression equation with 3 dimensions. We have 2 independent variables, as we see here. We have x1 and x2, and then we have our y variable sales here. Using just 2 independent variables, we have 3 dimensions. Using 3 independent variables, we would have 4 dimensions, and we can no longer visualize what that looks like. So we can use the same goodness of fit statistics, that R squared, that tells us how well our model fits the data, but we also need to consider how many variables we're using in a multiple regression equation. Why does this matter? Because if we have too many variables, then our model is incorporating more and more error every variable you add to the model. So we should always prefer a simpler model that gives a same or better prediction than a more complicated model. To incorporate the number of variables we're using, we use k to indicate how many variables we have. So we have n, our sample size, minus k minus 1. So the more variables we have, the more penalty we give to our adjusted R squared. Again, R squared tells us how well our model fits the data, and adjusted R squared is used for comparing models. We may have 5 different models using different variables, and in order to compare them, we give a penalty to those models using more variables because they're more complicated and maybe less reliable. Okay, so adjusted R squared is very useful, but it should only be used for comparing models, model comparison. All right, there are some warnings too. So you may have a really good model, but you're just looking at a spurious correlation. In other words, you should make sure that you have a real theoretical reason why your independent variables would be related to your y variable, your dependent variable. Okay. In this example, we're looking at a 2-scaled problem. So we have the black line here is the number of Nicolas Cage movies per year. And in red, we have the number of people who drowned per year. And if we look at the correlation, there's actually a really high correlation, a 0.66 Pearson's R correlation, meaning they're pretty highly correlated. When Nicolas Cage movies have more movies in a year, there are also more drownings in that same year. Is there a reason why these should be related? Hopefully not. Maybe people don't like Nicolas Cage movies, so they want to drown themselves, but I don't think that's the case. I think that it just happens. If we look at many variables, of course, we're going to find some that happen to move together just by chance. That is the example here. We call that a spurious correlation. They have a high correlation, but they're not actually related. Another problem with using regression is sometimes you'll see that people will use their regression analysis to predict outside of the data that they have. What I mean is, in this example, again, we probably shouldn't use regression to explain time series data. But here we have some time series data. If we use a regression model, we'll get a line that looks something like this or something like this. At some point, that line is going to cross 100%. So if we're plotting the amount of obesity in America, and we draw a regression line and predict, well, in 2048, 100% of people are going to be obese, this actually doesn't make sense, and it's not actually what your data is saying. Your data is only explaining the data that we have here. It's not good for prediction in the future where we don't have any data. Let's look at R and look at an example of regression, and I'll show you how we can analyze that. All right, here's our R code. I'm just going to clear our console. Boom. Okay, I already have this package installed, so I'm just going to run this line of code here, and that is going to help me load my Excel file. In this code here, I'm loading my Excel file into two objects, one called data with a capital D, one called data with a lowercase d. I like to do this every time I load some data set, because if I make a mistake and I want to recover my original data, I don't need to load it from the file again. I can just check my data object, and that will be my originally loaded data. Okay, so let's deal with our small d data and check the structure of our data. This tells us we have the name of the actor. We have the height of the actor and the weight of the actor. We have the gender and the origin. In this data set, we only have males. So in this case, this variable is not useful because there's no other category in the data that we have. If we look at the bottom, we have the origin being Western if they're a Western actor, or Korean if they're a Korean actor. Okay. And I got this height and weight just through Wikipedia, so I'm not sure how accurate these actually are. I'm sure the values in this data set are not actually very accurate. Okay, so I'm going to change these into factors. Why? Because we want to use these as factors when we are using a dummy variable. Again, this gender factor doesn't actually have much data in it. We only have one level, so it's not going to be useful. However, if we check our origin, we see that we have two levels, Korean and Western. If we wanted to check how much are in each group, we could use the function called table. And that table function will tell us how many are in each group, in case we wanted to know. Okay, I'm going to attach our data because this lets us refer to the columns as just the column names, and that makes it easier so we don't have to write the data set before every variable before we use it. So instead of saying data $origin, after attaching, we can just say origin, and that'll give us the same result. All right, so let's plot our data. Here I'm using plot. We have X and Y, so that means it'll create a scatter plot. Y limit will show me the limit here. I think this limit is a little bit too small, so let's change this to, let's say 20. Okay. So the data that I have here is a little bit different from the presentation. We actually have, I forget who this is. This might be So Jang-hoon, and I think this down here is Kang Ho-dong. So here we have a lot of people who are celebrities. Then we have these two entertainers who came from an athletic background, right? I believe he's a basketball player and he's a Siddham, like a Korean wrestling athlete. Okay, so given our data, I said our data is a little bit different. So the result in the PowerPoint may be a little bit different than the calculations that I show here. Here is our Pearson's correlation done mathematically. So I just want to show you, here we have X, weight, and Y is height, and we just follow that formula directly how we see it, and make sure to use parentheses to make sure that it's occurring in the same order of operations as it should. So let's just run our code. We get 0.68, which rounds to 0.69. Okay, so what is our correlation? We get the same result by using the function core, and this core test will give us the same result, but it includes a p-value. So here's the same correlation result, but we also have a p-value. Is this a significant p-value? What does this e minus 5 mean? It means that we have 4 zeros before the 1. So in other words, this value here is 0.00001093. Does that make sense? So these are the same value. This is just a shorthand way to show this value because it's very small. Okay, so is this value less than 5%? Definitely. So we have a significant correlation. All right, so let's calculate that beta 1 value using math. So using the same formula that you just saw in the lecture slide, we're just going to run this here using our weight as x and our height as y. And the rest, we're just following the formula directly. That gives us the beta 1 value of 0.32. So using this beta 1 value, now we can calculate beta 0 using, again, that same function that we had. The mean of height is our y bar. The mean of weight is our x bar. So let's calculate beta 0 as follows. We get 157.78. All right, so let's say we wanted to make a prediction for some individual who is not in our data set. So let's say that prediction is 80. Someone weighs 80 kilograms. We want to guess how tall they are. Well, that would mean our x value is 80. So we would simply take our intercept plus the beta 1 coefficient times the value we're predicting, and that will give us the predicted height of this individual given our model, 183.7. All right. So what is this value? This value is our y hat. So I can take all the values in our weight and calculate the prediction. Given their weight, what would I predict that their height is given their weight? So this is the weight of everybody in the model. This y hat isn't their actual height, it's the prediction of their height. So we can take the prediction of their height, y hat, and subtract it from the actual y bar. And using this function here, using this calculation, we can calculate an r squared value, about 0.47. All right, so that's complicated. It takes a long time and it's very tedious to write a mathematical equation. So instead, we can just use the function LM, meaning linear model. Since regression is a linear regression, it's a linear model. So we're looking at the y tilde, meaning in relationship to the independent variable weight. And our data is coming from the data set called data. Okay. All right, so if we run this, we have model A. This is our linear model. If I use the summary function, it gives us a summary of that linear model. And actually, we calculated them by hand, but using just this quite simple function here, it calculates all that information for us. We have our intercept, 157.78. We have our beta 1 value, 0.32. We have some uncertainty whether that's the correct value or not. We call that uncertainty the standard error. So here we have a standard error calculated from how big our sample size is and how much variation is in the data and so on. That gives us a t-value, a t-statistic value, and that t-statistic can be checked if it's significant or not. If it's significant, that means the effect that it has on y is not 0. In other words, that intercept is significantly different from 0. The effect of weight is significantly different from 0, meaning we can use this to predict our y. What's the first thing that we should check when we look at the results here? The first thing that I like to look at is the overall p-value for the F statistic. What is the F statistic? The F statistic tells us whether our independent variables are better at predicting y than just the average of y. In this case, we see that our independent variable, weight, gives more information than just using the standard average of y to predict y. All right, so if this is significant, it means we have a model that we can use. If I check my model, the next thing I might want to check is the R squared. How well does our model fit? Adjusted R squared is for model comparison using the same data, but because I only have one model right now, I can ignore the adjusted R squared. It gives us our F statistic, but really the only thing that's important down here regarding the F statistic is whether that F statistic is significant or not. That value of the F statistic depends on the degrees of freedom. So it's difficult to interpret just the F statistic because we also have to incorporate the degrees of freedom. Because of that, it's easier to just check that p-value, check if it's less than, in my case, is it less than 5%. All right, so these t values tell us if the coefficients are significant. In this case, this coefficient is just the intercept. This coefficient is the coefficient for beta 1. So it seems that both are significant. We can do a little easy check by just checking how many stars we have. All right, so that is our simple regression model. We can also create an ANOVA table from that model. Looks like this. It's basically just showing you how that F statistic is calculated. Okay? This one also confirms that our model is significant. If we want to plot, I like to plot our data. So here we have a scatter plot and a line through our scatter plot. We see that these two extreme values are one on either side. Okay. So let's use this function. We're going to plot. We're going to draw an AB line. An AB line is just drawing a line through our data. If we have a regression line, it'll draw a regression line through our data. And then I'm going to identify using X and Y. X is weight, Y is height, and I'm going to identify using the name variable. What does this do? It means I can identify who these people are. If I click near a specific observation, it will tell me who that person is. So here we have So Jang-hoon, is very tall, given his weight. And who's this person here? This is Gang Ho-dong. He's very, let's say his weight is, compared to the other actors here, his weight is a little bit higher given his height, or you could say the opposite. His height is a little shorter given his weight. Okay, and we could check each person here. Now, again, I don't know how accurate this information is. I just Googled this information. Okay, so let's clear our console. There's one more thing we can check, which is we can check the diagnostics of our model in detail. So if I just plot, this is the model, this is our linear model object. If I plot this, an empty plot shows up, but if I check the console, it says hit return to see the plot. So I'm just going to hit return. Okay, so on the X value, we're looking at the fitted values, basically the relationship between each point and the Y value. Then we have the residuals. How close were we? So if the residual is high, that means we predicted their height would be much lower than it actually is. It's a positive residual, meaning that the actual height is above our prediction. And then we see we have a value down here with a really big negative residual, and that is saying that this person has a height that's much lower than our prediction. You can probably guess who these two individuals are. Number 33 is our data index number 33, that's So Jang-hoon, and then we have individual number 32, this is Gang Ho-dong in our data. If I hit enter again, it shows me a different graph, and this is showing me the residuals, and one of the assumptions of our model is that the residuals follow a normal distribution. What a QQ plot does is it shows us, theoretically, we should have a normal distribution. So if we check our theoretical quantile, what a normal distribution should look like, and what our actual data is, what our actual residuals are, if that follows a normal distribution, every dot here would be exactly on the line. So any points that we see are above the line or below the line means they're not fitting the normal distribution exactly. In this case, we have two individuals. One person's residual is very negative, and we wouldn't expect to see a value this negative in a normal distribution. And one person is much too positive. So if we had a normal distribution, we wouldn't expect to see a value this positive given this data. In this case, if we look at the square root of the absolute value, it changes just everything to positive values. So it's showing us that we have 33 and 32. What this is useful for is if I'm going to delete an outlier, which outlier should I start with? Well, in this case, 32 is more extreme than person 33. In other words, Gang Hodong is more extremely far from our prediction than Seo Jang-hoon. So if we're going to delete one person, we should start with Gang Hodong in this example. And this is our last plot. This shows us Cook's distance. Now, I'm not going to describe Cook's distance in too much detail. I just want to describe how we can interpret this result. Cook's distance considers the leverage, how much the individual observation is pulling the line up or down based on how far on the edge that observation is. And it's considering residual, how far away that individual is from the line itself. So a problematic outlier is an outlier with high leverage, it's pulling the line, and a high residual, it's far away from the line. In this case, there's two people who are pulling the line. One is Gang Hodong, the other one is Seo Jang-hoon. We can see that if you look at this dashed line, we see a 0.5 and a 1. Any Cook's distance value more than 1 is very problematic. We can see that Seo Jang-hoon is just under 1 here, and Gang Hodong is a little bit farther. So that confirms that in this data set, Gang Hodong is a little more problematic for making our regression model. So I would recommend probably deleting that observation to make a better model. Okay, so this method here, I'm detaching my data and then attaching it again. Basically, I'm deleting Gang Hodong from my data set. So I use minus this row, minus any row where the name is equal to Gang Hodong. It's going to delete those rows, save it as data, and then we reattach the data. So I'm just going to run this code. It's just deleting him from the data set. Let's move down. Let's make a new correlation. This is the correlation without Gang Hodong in it. Again, we get a much higher correlation, and we can see the p-value is very significant. Now I can make a new regression model. Here's the summary of that new regression model, and we see that our R squared has increased to 0.61. And we can make our regression model. Looks like this. Here we have Seo Jang-hoon up here. It's still an outlier, but is it as problematic? It's a little less problematic because our line has been adjusted a little bit. You might want to check, maybe you could go back and delete this residual and see if you get an even better result. You would probably get a better result, but at what point are you going to stop deleting residuals? At some point you should stop. I would recommend to delete as few outliers as possible. All right, so how do we add a dummy variable to our model? We can quite simply, we have our height, y, we have our weight, x, and now we have a categorical variable, which is a factor type variable. Let's look at origin. We know it's a factor because at the end it says levels, telling us that we have these two groups. So these groups are organized alphabetically. So because K is before W, Korean becomes our first group, Western becomes our second group. That affects which group becomes our reference group. So in this case, we have our ANOVA table. Okay, I think this summary of the linear model is much more useful. So again, we can quite easily analyze this data. First, we check the p-value of our F statistic. It's significant, so we can use the model. So we should look into the model a little bit more. Next, I'll check my multiple R squared. How well does my model fit my data? Next, I'm going to check which variables are significant. In this case, my intercept is significant. That means that my intercept is significantly different from 0. My line doesn't cross 0. My weight is also significant. We can see we have 3 stars, meaning my p-value is more significant than. These 3 stars mean that my p-value is significant at the 0.1% level, so it's very significant. And my origin, and it tells me Western, is significant, meaning if my actor is Western, we should subtract 5.7 centimeters from their height on average. This example here is just plotting. So it's plotting one line for the Korean and one line for the Western. So we can see that the Western line is about 6 centimeters below the Korean line. So let's say, for example, someone has a weight of 90. How tall do we expect them to be? Well, if they're Korean, we might expect them to be around 192 centimeters. Whereas if we follow this line up, where it crosses our Western actor regression line, and then follow that over to see the Y value, we see that it's about 187. Okay, so we see that it's probably about 6 points less for each prediction, right? So that's how we use our dummy variable. That's how our dummy variable affects the prediction that we make for any given value of x. Okay, so let's look at our 2 models. We have 2 models. One model, we have a dummy variable. The other, we do not. All right, so how do I compare these 2 models? As we said before, the adjusted R squared is used to give a penalty if we have more independent variables to our model. What that means is if the independent variable that we adds a lot of useful information, then it's worth to add that extra variable. However, if we just add all the variables possible, we might have a lot of variables that are not useful. The R squared will go up, but the adjusted R squared is going to give a penalty for every variable that you add. So we should use adjusted R squared to compare our models. Our basic model is 0.45, and our adjusted R squared of our dummy variable model is much better, so our dummy variable is a better model. All right, so let's say we want to predict 2 people. We might have a data frame. So let's look at our data frame. Let's clear the console. Here's our data frame. Our data frame looks like this. We have 2 people, Cillian Murphy and Zhonggang. We don't know what their height is, but we know that they have the same weight. Again, I looked this up on Google. I don't know how accurate this is. All right, one is Western, one is Korean. So we have all of the variables that we have in our model. So that means we can predict their height if we don't know their height. So we can use the function called predict. We input the model, and then we input the data that we want to predict. Just make sure that the data that you want to predict has the same variables, weight, height, origin, and then this predict will work. So let's use that predict function. Use that predict function in Model D. So using Model A, we predict that. Okay, let's look at our data. First is Cillian Murphy, next is Zhonggang. So number 1 is the prediction for Cillian Murphy. Using we get the same prediction for both because in our first model, it doesn't consider whether they're Western or Korean. If we use our second model, we see that the Western actor is expected to be a little shorter on average than our Korean actor, given the same weight. How accurate are these models? You can go and check their actual heights I would guess that this is probably not a great model. I'm just using it to illustrate in a very easy way with data that you can understand how these models work. Okay, so don't use this for accuracy. This is not an accurate representation of these actors or entertainers, but I think they're familiar to many people, so it makes it a very easy data set to use. All right, so you should always be aware of what is your data set and what does that data set actually represent? What is the population that you're actually representing with your model? Could I use this model to predict my weight? Sure. Would it be a good model for predicting my weight? Definitely not. I'm not an actor. I don't look like any of these actors in my data set. So what is the population that my data set is predicting? It's probably a very small population of maybe actors or famous people. I'm not sure exactly. So consider theoretically whether your model actually represents the population that you're hoping that it does. So my goal here was to give you kind of a practical explanation of a simple regression model. You can go much deeper into regression. There's a lot of things that we didn't actually explain here. I just wanted to explain it in a way where you have a basic understanding of how you can use the model using R. Hopefully that was useful. Okay, so this concludes lesson 10, regression modeling. I hope this video has been useful to you in some way. Good luck on your research. This is part of the lecture series Applied Statistics Using Programming. And my name is Dr. Ian from Sogang University. I hope to see you in a future video. Thank you for watching. So if I were to color my scatter plot by what color the actors are, no, that's a bad one. If I, look at this beautiful light switch next to my head. Bye.